How fast is a cliff diver falling the exact moment they hit the water? Or how quickly are a company's costs going up the instant they decide to produce just one more item? See, these aren't questions about averages over time. They're about change happening in a single, specific moment. To even begin to answer questions like that, we need to dive into this one really powerful idea from calculus. You can think of it like a universal key, one that unlocks the secrets of change in fields that seem totally different, like physics and economics. So here's our game plan for this explainer. We're going to start with that core problem, then we'll find the mathematical tool that cracks it open, and then we'll see how that one single tool helps us understand change in all these different worlds. All right, let's get into it. We'll start with the fundamental challenge. How do we get past simple averages to actually measure change as it's happening, right now? Think about it like this. Calculating your average speed on a road trip, that's pretty easy, right? It's just your total distance divided by the time it took. But what about that number on your speedometer? That's your speed at one specific instant. Pinning that number down mathematically, well, that's a much trickier problem. And it's exactly the problem we're here to solve. And the tool that solves it is called the derivative. This is it. This is the central concept that lets us figure out an instantaneous rate of change. We can actually see the idea we already know pretty well. The average rate of change, like your average speed on that trip, is really just the slope of a line that connects two different points on a graph. We call that a secant line. Simple enough. But to find the speed at one single instant, you have to imagine the time between those 2 points shrinking down to basically nothing. On the graph, this does something amazing. It transforms that secant line into something totally new, a tangent line. That's a line that just barely skims the curve at a single point. This visual really captures that leap we're making from average to instantaneous. So as we slide point Q closer and closer to point P, you can see that secant line pivoting. Its slope is getting nearer and nearer to the true rate of change right at point P. In calculus, this process has a name. We're taking the limit. As that distance between the points gets to 0, the secant line becomes the tangent line. And that final value, the slope of the tangent line at that one single point, that is what we call the derivative. It's the mathematical way of saying instantaneous rate of change. Okay, so we've got our mathematical tool. Now for the really exciting part. Let's see how this one idea unlocks our understanding of the real world. And we'll start with physics, which is where these ideas were first born. And here's where it just gets amazing. The exact same mathematical operation describes two totally different physical laws. If you take the derivative of an object's position, you get its instantaneous velocity. If you take the derivative of electric charge, you get electric current. Get that? It's the same math describing two different realities. Now let's just jump from the inanimate world of physics all the way over to the living world of biology. Can the same idea really apply here too? Oh, absolutely. If we track the number of individuals in a population over time, the derivative gives us the instantaneous growth rate. So it's not the average growth over a year, but the precise rate of growth happening right now. And this is a perfect example of why this is so useful. I mean, a real population changes with individual births and deaths, right? That would make for a really choppy, jerky graph. But for a really big population, like this bacteria colony, we can model it with a smooth curve. And that lets us use the derivative to find the exact growth rate at any given moment. And it doesn't stop there. This same idea, the derivative, is used to analyze how fast blood is flowing in an artery, or the rate of a chemical reaction. It's literally the calculus of life itself. Okay, so from life sciences, let's pivot to the world of money. It might seem like a huge leap, but let's see how the exact same idea helps us make sense of economics. In economics, if a company has a function that describes its total cost to produce X number of items, the derivative of that function gets a special name, marginal cost. It's the instantaneous rate that the company's cost is changing at a specific level of production. So why does that even matter? Well, because the marginal cost gives a company a really good estimate of what it's going to cost to produce just one more widget. And that is critical information when you're making decisions about pricing and how much to produce. So we've just toured through physics, biology, and economics, and we saw the same core mathematical idea pop up in every single one. This is the incredible unifying power of this concept. Let's just step back and appreciate this for a second. The sheer power of this one idea. The derivative gives us velocity in physics, reaction rates in chemistry, population growth in biology, marginal cost in economics. You can even use it to model the rate a rumor spreads in sociology or the rate of learning in psychology. It's a truly universal language for describing change.
You know, the mathematician Joseph Fourier really said it best. Mathematics compares the most diverse phenomena and discovers the secret analogies that unite them. The derivative is one of the most powerful examples of that truth. It's a single, abstract idea that reveals the hidden connections in the way our entire world changes from one moment to the next.